In this deep reinforcement learning tutorial, you are going to learn how to code a soft actor-critic agent in the PyTorch framework starting from scratch. Let's get started. Before we begin, a brief announcement. This content comes from my course on Udemy on actor-critic methods, which is presently on sale. If you're also looking for how to learn deep Q-learning methods, that is also on sale. And in both courses, I show you how to turn papers into code. So let's go ahead and get started. We want to begin with the agent's memory, which is its replay buffer. And there are a number of ways of doing this. I like to use NumPy arrays. They're just a little bit more easy to understand and a little bit easier to get the meaning of when you see them written in code. So we're going to stick these in their own class, and our initializer is going to take a few parameters, a maximum size of the memory because we don't want it to be unbounded, and this will typically be something like 1,000,000 transitions, an input shape which will correspond to the observation dimensionality from the environment, and the number of actions. Now, in this case, we're going to be dealing with a continuous action environment, and so number of actions means the number of components of that action. So we'll go ahead and save our variables, and we need to instantiate a memory counter which keeps track of the position of the first available memory. And we're going to go ahead and start initializing our memory. So that will be shape mem size by input shape. We'll also need a new state memory that keeps track of the states that result after our actions. And that is functionally the same size as the state memory. The number of actions, the action memory will have shape mem size by n actions. Again, those are a number of components of the actions. A reward memory to keep track of the rewards the agent receives with each step of the environment. And that's just going to be an array of scalars. And then we have the terminal memory. Now, the reason we need this is because the value for the terminal state is identically 0. And we're going to be storing the done flags from the environment as a way of setting the values for those terminal states to 0. And the data type on that is going to be a Boolean. Our first function is to store a transition, and that'll take a new state, action, reward, new state, and terminal flag as input. The first thing we want to do is figure out where our first available memory is. So we're going to get that index by taking the modulus of the memory counter and the memory size. Evidently, I can't talk and type at the same time. And then we're going to set the NumPy arrays at that index equal to the parameters that we have passed in from our function. Terminal memory, state, new state, action, reward, done. I believe that is it. And then finally, we want to increment our memory counter by 1. So next, we want to handle the function to sample our buffer. And that will take a batch size as input. And alternatively, you can make the batch size a member variable of the replay buffer. It doesn't really matter. The first thing you want to know is how many memories have you actually stored in your buffer, and it's given by the minimum of the mem counter and the mem size. And then you want to select a sequence of random integers between 0 and that maximum memory. And then go ahead and sample those memories. Of course, I forgot the self here. Remember memory sub batch. and dones. All right, so that wraps up our replay buffer. Now we're ready to move on to the relatively hard part of the problem, which is the deep neural networks. So before we proceed, I want to give a brief, theoretical overview of what it is we're trying to accomplish with soft actor-critic. So in the soft actor-critic algorithm, we want to solve the problem of how to get robust and stable learning in continuous action space environments. You can also use algorithms like DDPG or TD3 for continuous action environments, and TD3 in particular works really well. It's on par with the soft actor-critic algorithm. They were developed concurrently by separate groups, so they're kind of comparable algorithms in terms of their quality. DDPG falls a little bit short. It doesn't do quite as well as the other two. The basic idea in soft actor-critic is that we want to use something called the maximum entropy framework. Entropy just means disorder in this case, so it's going to add a parameter to the cost function, or rather it's going to scale the cost function in such a way that it encourages exploration, but it does so in a way that is robust to random seeds for your environment, as well as episode to episode variation and starting conditions. So when you do lots of content in deep reinforcement learning, you'll see that if you plot the total rewards over time, you'll end up with lots of squiggles from episode to episode. Even if you do see an upward trend over time, it generally squiggles up and down as it has a general upward trend, whereas soft actor-critic tends to be a little bit more smooth. It has less of a problem with the episode to episode variation, and that's due to the fact that it is maximizing not just the total reward over time, but the stochasticity, the randomness, the entropy of how the agent behaves. As far as the neural networks we're going to need a network to handle the actor, which is the policy, and we're going to be handling how the agent selects actions differently in this particular technique than with respect to something like DDPG or TD3. In those two cases, the neural network output the action directly. In this case, we're going to output a mean and standard deviation for a normal distribution that we will then sample to get the actions for our agent. We will also need a critic network that takes a state and action as input and says, hey, actor, I think the action you took was really good, or hey, actor, I think that action was terrible. And then we're also going to have a value network that says this state is valuable or that state is not valuable. And there will be an interplay between the three to figure out for any given state, what is the best action, what is the best sequence of states to access so you can know what actions to take over time. But we do need three networks, and we are going to define those presently. So we will need OS to handle model checkpointing, because with the the inverted pendulum environment, it learns relatively quickly, but for other more complex environments, it learns rather slowly. We need torch, functional, need NN for our layers, our optimizers, and we will need our normal distribution as well as NumPy. So we will start with the critic network, and that derives from nn.module. This is just standard fare for PyTorch. We will take a learning rate, I'll call it beta, number of input dimensions from our environment, dimensions for the first and second fully connected layers. I'm going to go ahead and rewrite things on the fly. So we're going to just default these to 256 because that's what they use in the paper. A name for model checkpointing and a checkpoint directory. And the first thing we want to do is call our superconstructor and start saving our parameters. And so we're going to have a checkpoint directory and file for our network that handles model checkpointing, as I said. So we'll have to be very careful to do a make directory before we run the program, otherwise it's going to complain. The next thing we want to do is define our neural network, and that will take input dim sub 0 plus and actions as input. And again, so if this is mysterious to you, the reason we have to do this is because the critic evaluates the value of a state and action pair. And so we want to incorporate the action right from the very beginning of the input to the neural network. Alternatively, in deep deterministic policy gradients, you can just pass in the state to the first input layer and then pass in the action later. It doesn't really matter. It's just a little bit easier to handle the addition of the state and action states from the very beginning. But again, we have to do that because the critic evaluates the value of a state action pair. So then our second fully connected layer goes from FC1 to FC2 DIMMs, and then we have an output, which is a Q, and that is a scalar quantity. So now we need our optimizer. What are we going to optimize? The parameters of our deep neural network with a learning rate of beta. If you don't know where this self.parameters comes from, it comes from the fact that we are deriving from nn.module. It is an inherited method from the base class of nn.module. Next thing we want to handle is the device for our computation. If you have a GPU, you definitely want to take advantage of it. And finally, we want to send our entire network to our device. Next, we have to deal with the question of feed forward. So how do we feed forward a state and action pair through our critic network? That'll take a state and action as input. And so we will say that the action value is the feed forward of the concatenation of the state and action along the batch dimension through our first fully connected layer. I think I said that right. Action value, then we can activate it. Then we can pass that through the second fully connected layer, activate it, and then pass it through the Q layer to get the final value for the state action pair. And then Q and return Q. Next, we need a couple functions to handle saving and loading model checkpoints. So we were just going to save the state dictionary for our model in the checkpoint file. And then we're going to do the inverse operation for loading. All right, so that wraps up the critic network. I'm going to do the value network next. I'm kind of changing the order of stuff as I go around here. So the value network is next. That's the easiest of the three. And our initializer is going to take a few fewer parameters. We need a learning rate beta, input DIMMs, FC1 and FC2 DIMMs, and I believe that is it. No, we need the name. I'm going to run into a problem, aren't I? Let's do this. Just realized I probably have an issue here with putting my positional and keyword arguments all mixed up. We'll give it a default of critic. All right. Come on. So now we can go ahead and save our parameters after calling our super constructor, of course. And we don't need the number of actions here because the value function just estimates the value of a particular state or set of states. It doesn't care about what action you took or are taking. And then we have our network. And that's just a very simple neural network. We're going to go from input DIMS to FC1 DIMS. Second connected layer. And an output layer, and that'll be a scalar quantity, so it's just FC2 DIMS by 1. And of course we also need an optimizer and device for this network as well. And then we'll send everything to the device. The feed forward function is pretty straightforward. We want a state value, and then we want to activate it, and pass it through our second fully connected layer. Activate it again. Get our output and return it. And then we also want save and load checkpoint functions. I am going to copy and paste those because that is just significantly easier. And then we want the actor network. Now this is the relatively hard part of the problem because we're going to have to handle sampling a probability distribution instead of just doing a simple feed forward. So we're going to start with our initializer, of course. Takes a learning rate alpha, input DIMS. I'm going to default this to what we use in the paper. Max action. Let's not give that a default value. We will also need a num actions, a name, and a checkpoint directory. Now the point of the max action, oh sorry, this stuff is a little bit hard for you to see, isn't it, because of my ugly mug. So the point of the max actions is that the deep neural network is going to be constrained, or rather our choose action function, or sorry, our policy sampling is going to be restricted to ±1 with a tangent hyperbolic function, but an environment may very well have an action bound that is greater than that. It may have an action bound of 2 or 3 or 5 or whatever, and so you want to output you want the output of the deep neural network of the sampling function to be multiplied by the max action, so that way you get the appropriate range of actions for your environment. So we will call our superconstructor and save our variables. We'll need number of actions. We need our max action, and we also need something called reparameterization noise. Now, the need for the reparameterization noise will be a little bit more apparent when we handle the calculation of the policy. It's going to be there to serve a number of functions. First of all, it's going to make sure that we don't try to take the log of 0, which is undefined. That'll break the software, so we need a noise factor for that. But first, let us define our deep neural network. Input dims by FC1. And then we have two outputs, a mu, which is going to be the mean of the distribution for our policy. And that will have as many outputs as we have components to our actions, and a standard deviation. And then again, we need an optimizer and device and to send the network to the device. Next, we will handle our feed forward. That takes a state as input, and I'm going to call it prob for probability. It's kind of a misnomer, I suppose, but sue me. And then we'll say mu is that. And then we have to do something a little bit mysterious. It makes sense if you think about it. The next step is to clamp our sigma. And the reason is you don't want your distribution for your policy to be arbitrarily broad, right? The standard deviation determines the width of your distribution effectively, right? The mean is the center point and the standard deviation is its width. You don't want that to be really, really broad. You want that to be some finite and constrained value. Now, the authors of the original paper, if you take a look at their code, they use a clamp, which makes a lot of sense because it's computationally cheap. But they use a lower end of -20 and a higher end of +2. Now, I don't know how they came about that. I'm certain it's just a consequence of experimentation. But if you use a negative value for your standard deviation, or sorry, a negative bound, then you end up encompassing 0, and the PyTorch framework doesn't like it if you get a sigma of 0. So we're going to use a very small number, which is the reparam noise, 1 by 10 to the -6. And a max of 1, so between 0 and 1. You can also use a sigmoid function here to have a nonlinear activation between 0 and 1, and that works just fine. The issue is that it's a little bit slow in terms of computational speed, so the clamp is much faster, and this is already a computationally expensive algorithm, so I make the optimization to use the clamp function. So then once you have calculated them, you want to return the mu and sigma. And the next, we have to handle the calculation of the actual policy. Now, if you're new to deep reinforcement learning, a policy is a probability distribution that tells you the probability of selecting any action in your action space given some state or set of states. So you're in some state, you have some available actions. What's the probability of choosing each? If you have a discrete environment, it's an environment with a discrete action space, then it's pretty simple. You just assign some probability to each of those actions, and it's a discrete probability distribution. But if you have a continuous action space, then we need some sort of distribution like a Gaussian, in this case a normal, which is how we're going to handle this. And we have some parameter here called reparameterize. Don't worry about that too much. I go more in depth on that in the paper because it's a trick the authors use. Don't worry about that for now. It's not something to be overly concerned about. It just changes something down here. So we want our actual distribution that is mu and sigma, a normal distribution defined in terms of mu and sigma. If we're going to reparameterize, then our actions are going to be a sample. Sorry, an R sample. And what this does is there are two sample functions for the normal distribution. One gives you just a normal sample. The other one gives you a sample plus some noise. So we're adding some noise, some additional exploration factor to the actions. If we're not reparameterizing, we just want to sample the distribution. Next, we want to get our action for our agent, and that is a tan hyperbolic activation multiplied by the max action, because remember, the environment could very well have a maximum action beyond plus or minus 1. And to make PyTorch happy, we have to send that max action tensor to our device, because we have to have the same data types for everything in the entire graph, and we're dealing with CUDA tensors elsewhere, so this has to be a CUDA tensor as well. Next, we want the log of the probability, and this is for the calculation of our loss function. It doesn't go into the calculation of what action to take, but rather the loss function for updating the weights of our deep neural network. abilities.log prob, that's just a built-in function, and we want to take it on the actions, not the action, so plural, not singular. The reason is that the singular case here is proportional to the tan hyperbolic and the max action of our environment, whereas the actions are what we actually sampled from the probability distribution. So when we come here, we're changing that, so we didn't actually draw the tan hyperbolic from the distribution. Very important. Then you want to subtract off the log of 1 minus the square of the action plus some reparam noise, because this could very well be 1 minus 1, which would be 0. Log of 0 is undefined. And then we want to take the sum. The reason we want to take the sum is because we need a scalar quantity here in the calculation of our loss, and this log probs will have a number of components equal to a number of actions. And this line here comes from the appendix of the paper. It's just how they handle the scaling of the action. You know, they do this tan hyperbolic activation, take the log prob, and then subtract off this term here. And then we have to do this because the PyTorch framework outputs something that has dimensionality corresponding to the number of components of your actions, and you need a scalar quantity for your loss. Okay, so now that it's clear as mud, again, I go into more detail in the course. It's a little bit slower pace, and it makes more sense when you see it in the context of the analysis of the paper. But we have limited time here, so you just get the quick and dirty version. If you want, you can read the paper. It's very easy to find. It's on the archive. It's a very dense paper. That's where my course adds value, is that I help break it down for you, but it's certainly readable by the advanced and dedicated student on their own. So you don't need me if you're really, really good at this, but I do help. So that is it. Excuse me, we need our functionality to save and load checkpoints. We'll just yank and paste those. And now I believe we are done with our networks. Okay, now we can handle the actual agent itself. So we'll begin with our imports. We will need OS, Torch, we will also need NumPy. We will need our replay buffer. We will need all of our networks. And we're going to put all of our functionality in an agent class. We will need an alpha, a beta. You know what? Let's do this. Alpha. I'm just going to use the defaults from the paper right away. Use a default of 3 by 10 to the minus 4 for all of the networks. I'm just going to use something like 8 for the input DIMMs, none for the environment, and a gamma of 0.99. Sorry, we also need a bunch of other stuff like and actions, max size. That is 1 million transitions for our memory. Layer 1 size. A batch size. That is a default of 256. And a reward scale of 2. So the reward scaling is how we're going to account for the entropy in the framework. Basically, we're going to scale the rewards in the critic loss by some factor, in this case 2, because that works for our environment. The authors experiment with a wide variety of reward scaling factors, and that is going to depend on the number of action dimensions for your environment. So we have a simple environment for this tutorial, so a reward scale of 2 is sufficient. So we're going to want to save the relevant parameters, and it looks like I forgot my tau. So the tau is the factor by which we're going to modulate the parameters of our target value network. So we're going to have a value network and a target value network, and rather than do a hard copy of the value network, we're going to do a soft copy, meaning we're going to detune the parameters somewhat. This is reminiscent of DDPG and TD3. Replay buffer, max size, actions. We also need our batch size. We need our n actions, and then we need our networks. So our actor, that's an actor network. And we need alpha and input DIMMs. We already have strong defaults for our layer sizes, so we'll use n actions equals n actions. The name is going to be equal to actor, and our max action is going to be equal to env.action space dot high. So I'm kind of wincing here because I did some things differently in the course where I did a lot of experimentation with environments, and so I have some other parameters in here for my agent that wouldn't really make sense for this tutorial. So I'm doing some changes on the fly. Next, we're going to use 2 critics. So I said there's a critic network, but in reality there are 2, and we're going to take the minimum of the evaluation of the state for those 2 networks in the calculation of our loss function for the value and actor networks, I believe. So we have critic 1, and that is a critic network that takes beta, input DIMMs, and actions equals n actions, name equals critic 1. And that doesn't need a max action. Similarly for critic 2. Good grief. All right, and then we need a value network. And a name of value. I think that's all the parameters we need for the value network, because we don't have number of actions. We already have strong defaults for the layer sizes. Then we need our target value network. And the only real difference there is the name. And then we need our reward scaling factor. And to call a function called update network parameters, what this will do is it will set the parameters of our value network, our target value network, exactly equal to the values of the target network to start. And on every other update, we're going to slightly detune them. We're going to update them with a slightly detuned version. So now we need a function to choose our action. That takes an observation of the current state of our environment as input. So let's go ahead and turn our observation into a PyTorch tensor and send it to our device. So it is a CUDA tensor. And then we're going to feed that state forward through the sampling function for our actor to get the actions and ostensibly or nominally the log probs back, but we don't care about the log probs, so we just use a blank state. And we're not going to reparameterize for our action selection. Now, then we're going to return it. It is a CUDA tensor, so we have to send it to the CPU. We have to detach it from the graph, and we have to turn it into a NumPy array and take the 0th element. That's one of the quirks of the PyTorch framework. It's something we can live with, though. Then we need an interface function between the agent and its memory. So we'll take a new state, action reward, new state, and done flag as input. And then we're going to store that transition. All right. Oh, I don't need a colon there. Don't know what I was thinking. And then I'm going to write let's get the 2 bookkeeping functions out of the way. Let's do update network parameters. Now, this is kind of a clunky function. So if tau is none, then we're going to set tau to the stored value for our agent. And the reason we have to do this is because at the beginning of the simulation, we want to set the values for the target network to an exact copy of the value network. So the target value network should be an exact copy of the value network. But on every other step, we want it to be a soft copy. So I use this mechanism with tau equals none to facilitate that. And then my solution here is kind of ugly as well. So we'll say target value params. Basically what I'm going to do is create a copy of the parameters and modify them and then upload them. Value.named parameters value state dictionary equals dictionary and then value state dictionary of value params for name in state dictionary. We're going to set the parameter to tau multiplied by the state dictionary and 1 minus tau multiplied by target value state dictionary clone. And then we're going to load that dictionary, self.target value load state dictionary value state dictionary. Okay, so that is the function to update, to perform the soft or hard update for the value network parameters. Then we need 2 functions to handle the interface with the agent's network save model checkpointing functions. So we'll say def save models value and then similarly we need a function to load our models. Okay, now, so the simple stuff is over, and now we have to worry about the actual learning functionality of our agent, and that is the heart of the problem. So the first thing we want to do is see if we have filled up at least batch size of our memory, and if not, we're not going to bother learning. We're just going to go back to the main loop of the program. And if we have filled up our batch size, we're ready to go ahead and start learning. The first thing we want to do is sample our buffer. And then transform those NumPy arrays into PyTorch tensors. Now you may ask, why don't I just handle this in the replay buffer class? And that's because I want the replay buffer to be framework agnostic. I want it to work with Keras, TensorFlow, and PyTorch. So it just should be stored or written in terms of NumPy arrays or some other structure that is, you know, ambivalent about whatever type of tensor we choose to use later. And so I'm going to turn them into CUDA tensors. We will need our state. I'm setting all of these to the actor device. It doesn't really matter because all the devices for the networks are the same. It should be new state, otherwise this will not work. That will be horribly broken. It would be a tough bug to hunt down because it's not something I would think to check. And I'm being very pedantic about the data types here because PyTorch is quite particular, and so I want to be sure that I don't, you know, flag an error when the software is running later. So next we have to calculate the values of the states and new states according to the value and target value networks respectively. So value, state, and I have to collapse along the batch dimension due to the way the loss is calculated. So you'll see a dot view -1. That just means it returns a view of the tensor with one less dimension, and it collapses it in this case along the batch dimension because this will return a tensor of tensors, which doesn't make sense for a tensor of scalars. You know, you don't want each of those inner scalars to be wrapped in brackets. Doesn't make any sense. So you just return a view along the -1 direction. Target value along the -1 direction, and if that is mysterious to you, get rid of it and print out the shapes of stuff to the terminal, and that'll make it a little bit more clear. And then everywhere that the new states are terminal, we want to set the value to 0 because that is just the definition of the value function. And I'm kind of looking at this funny because I noticed that here I use basically the call method, and then down there I do the dot forward, which is pretty funny. So I kind of switched up my nomenclature halfway through the learning function, and I didn't realize it when I was doing the video for the course. It's a little bit funny. It doesn't affect the execution of the program. It doesn't really matter. It just looks weird. So the next thing we have to do is we have to get the values. We have to get the actions and log probabilities for the states according to the new policy, and not for the actions that were actually sampled from our buffer. We'll use those later, but in the calculation of the loss for our value network, as well as the critic network, we want, the value network and the actor network, we want the values of the actions according to the new policy. And we don't want to use the reparameterization trick here, but we do want to use the view. And then we're going to need the Q values, the critic values, under the new policy. state actions. Notice I'm using actions and not action. Then we have Q2 new policy. State and actions. Our critic value is then going to be the minimum of those two. If this is mysterious, we do this because you actually improve the stability of learning. So if you're familiar with Q-learning, you know that there is the problem of the overestimation bias. So overestimation bias happens not just as a consequence of the fact that you're using a max over actions in the Q-learning update rule. It happens also as a consequence of using deep neural networks. So they kind of demonstrate this conclusively in the TD3 paper. And so one way around that is to make a direct analog of the double Q-learning update rule by taking the values of the states and actions with respect to two different Q functions and then taking their minimum instead of a maximum. So it's a pretty clever solution. You can see more of that in the video on TD3, but that is the basic idea. And of course we want to return a view and collapse along the bash dimension here, and then we can go ahead and calculate our loss and backpropagate. So our value target will be the critic value minus the log probs, and then our loss will be 0.5 multiplied by f.mse loss value and value target. Then we want to backpropagate, but I don't know if you're aware of this option for the backpropagation function, but you can actually retain the graph between backpropagations. By default, PyTorch will discard the graph calculations every time it backpropagates, and we don't want it to do that because there's coupling between the losses for the various deep neural networks, so we want to keep track of that graph for the losses for the value and actor networks. And then we say value optimizer step. So that handles the value network loss. Now we're ready to deal with the actor network loss. And so we start by doing another feed forward to get the actions and log probs. But in this case, we do want to use the reparameterization trick. Then we'll say log probs view -1. It's otherwise identical to that other chunk of code up there. It's just that we have to do the reparameterization trick here. So Q1 new policy. In fact, I'm just going to copy this code. Now, if you wanted to be a good little data scientist, you would stick this in a separate inner function, but I included all of the code here twice just for clarity. So then we say actor loss log probs minus critic value, and then we say actor loss t.mean, and then we want to zero out our optimizer, backpropagate, again with retain graph equals true, and step our optimizer. Okay, so now we only have one last thing to deal with for this particular function. We have to deal with the critic loss. So this one is a little bit more straightforward. It's more similar to what you would get with something like Q-learning. So we'll say let's go ahead and zero out our gradients for both critics and calculate this quantity called Q hat. That's our scale factor multiplied by our reward plus gamma times value underscore. So that scaling factor handles the inclusion of the entropy in our loss function. So that's what helps to encourage exploration. And we also, of course, need gamma multiplied by the value of the states resulting from the actions the agent took. So then we have Q1 under the old policy. This is where the actions from a replay buffer come into play. critic1.forward state action view -1. It would help if I spelled action correctly. And note again, I am using the action from the replay buffer here, hence it is under the old policy, not the policy as it is right now. 1 loss equals 1/2 of the mean squared error loss policy and Q hat. And then we'll take the sum of the two. The sum, sorry. And back propagate. And then step our two optimizers. And finally, we want to update the network parameters for our value function. Okay, so that is incredibly long, but we're still not quite done yet. We have to handle the main loop to test everything out. So let's go ahead and write that. But really quickly, before we do that, let's do the following. Let's do pip install pybullet envs, and this will give us the, it's pip install pybullet. That will give us the pybullet package, which of course I already have. Then we can come into the main file and say import pybullet envs. This will give us access to the pybullet environments. If you're not familiar with it, pybullet is an open source 3D rendering and physics engine. It's really cool. It has support for virtual reality. It has built-in OpenAI Gym compliant environments. It has a couple built-in agents you can actually use. So it's a really neat package. It's something you can go do a Google search for and look up the documentation and start playing around with it if you're into that kind of thing. I'm using it here because it is it executes quickly and it has a non-trivial, the inverted pendulum is a little bit non-trivial. You can use the cart pole if you want. The continuous cart pole, but this is just a little bit less trivial. So we're also going to need gym, we'll need numpy, we'll need our agent, we will also need plot learning curve. So that is just a utility function I have that does a plot with some axes labeled. I'll have to copy it over into this directory. If you want it, do a clone of my GitHub and you'll have it. And if not, just do, instead of plot learning curve, just do a plot from matplotlib. So our environment will be gym.make inverted pendulum bullet environment v0. Our agent. So we already have the strong defaults for our alpha, beta, reward scale. We need our input dimensions, and that is env.observation space.shape. We need our environment, and then we already have strong defaults for everything except the number of actions, I believe. Action space shape sub-0. We already have the layer 1 and layer 2 sizes, batch size. I believe tau we have a strong default for. Okay, so that should work, otherwise we'll get an error. We only need to play 250 games for this environment. And inverted pendulum.png. In fact, yeah, we'll do that. I like to split it into a figure and a figure file, file name into a figure file. just how I do it. It's probably not even the best way to do it. So we want the best score, which would be the bottom end of the reward range, and a list to keep track of the scores the agent receives, and load checkpoint. So this will determine whether or not we want to load a pre-trained model. And if you do, then what do? So if load checkpoint, agent.load models, and env.render mode equals human. So what this will do is it'll render, the agent playing the environment to the screen. Then we'll say for I in range and games, observation equals env reset, done equals false, score equals 0. While not done, observation underscore score plus equals reward, agent dot remember if not, load checkpoints. So we only want to learn when we aren't trying to evaluate an agent. Sounds like my toddler's upset about something. Then we set the observation to the new state. So then at the end of every episode, we append the score we achieved and calculate the average score. As the average of the previous 100 games, and say if average score is greater than the best score equals average score. If not, load checkpoint. So if we're not evaluating, then save the model. Okay. So sorry, my toddler is throwing a fit. His poor grandparents. Episode I, score percent on F, score, average score, average score. All right, so that'll print some basic debug information to the terminal. And then if we are not loading a checkpoint, then we want to go ahead and plot our learning curve. And games, and plot the score history. Okay, so that is it for our main file. Let's see how that works. So I want to do a make_dir plots, make_dir temp. Do I need temp/soft actor-critic? I think I do. What else do I need? That's for the saving models and plots. Oh, and I need to get my utils file. So I do not have my utilities. So we will do a copy. This is just something you shouldn't do because this is local to my machine. Code courses, which you can't see. That's fine. Actor-critic methods, soft actor-critic utils. Okay, copy that here, and now I have my utilities. Okay, now we're ready, I think. Let's see how many typos I made. Value agent has no object, no attribute value optimizer. It's because it's value dot optimizer, not value underscore. So that is in PyTorch line 95. Value dot optimizer. Okay, try it again. I misspelled reparameterize in line 1. Whoops. I want to do vim, not try to run it again. Let's do vim. That's in line. I'm getting a spam call. All sorts of chaos today. Line 101. reparameterize. I think that's right. All right, so there it goes. So I'm going to go ahead and pause the recording here and come back when it finishes running. All right, so this has finished running, and you can see that it is in the process of learning. So there is a little bit of run-to-run variation. When I run this for the course, it achieves a score of 1,000 within 250 games. You can see here it was generally trending up when the last 30 or so games scores were going sky high towards 1,000. So it learned a little bit slower on this particular iteration. Sometimes it learns a little bit faster, sometimes a little bit slower. Despite the fact that the algorithm seeks to minimize run-to-run variation and improve stability, there is some run-to-run variation and, not rock solid stability. That's to be expected with deep reinforcement learning. But again, to recap, the fundamental idea behind soft actor-critic is that we are using a maximum entropy reinforcement learning framework, but the entropy comes from scaling the reward factor. This encourages exploration or encourages exploitation depending on that scale factor. As that scale factor grows, then the signal to exploit grows. As the reward scale decreases, then the tendency to explore increases. So it is a way of fine-tuning the performance of the model, and in fact it's the only real parameter you have to play with for the performance of the agent. You don't have to tune learning rates, you don't have to tune the number of neurons for your hidden layers. You just tune that reward scale to get an idea of how to improve the performance of your model. If you want to learn more in depth on this, if you want to learn more in depth about other deep reinforcement learning models such as TD3, DDPG, double Q learning, dueling double deep Q learning, check out the links in the description. I sell courses on all these topics through Udemy, and they're on sale right now. If you can't afford that, then by all means, please subscribe because that is free. Hit the bell icon so you get notified when I release new content. Hit a like, leave a comment, and I'll see you in the next video.